In this lesson, we're going to look at how using the type of setup like magnetic fields and electric fields scientists used or physicists used to figure out the nature of the atom. If you go back to the early theories about atoms, one of the first ones was the John Dalton theory, his model. He presented his theory that the elements of the periodic table were made of atoms in 1803. The main reason he was proposing this idea was to be able to explain the chemistry he was studying. And so here we have a picture of a representation of what it kind of looked like. And really erase this little part here. Draw a circle. There's the atom. He believed that atoms were solid pieces of matter that could not be broken down any further, so they're fundamental in nature. This is why his model is also referred to the solid sphere model, or some teachers or some people call it the billiard ball model. You can imagine a billiard ball and what it looks like. Here's our 8 ball, and that's what atoms look like. His model was able to explain the way he saw chemical reactions, but the model was really unable to prove that matter was made up of these atoms here. And so it wasn't until the invention or the creation of a thing called the cathode ray tube. Um, some people call it the CRT tube. It's on the old televisions where it's your old TV how it works. CRT tube. And so a CRT tube is just a vacuum tube. So it's just a tube of glass. All the matter sucked out of it. And so we have our tube right here. Imagine that was glass, and then we had some metal, and we have a cathode, and we have an anode, and what we have to do is attach them using some metal, some wires. We could have some voltage here. So imagine we can change that voltage. What happens is that the metal gets excited, and what we have released is this ray. And we call those the cathode ray. Now, why is it called the cathode ray? Well, it's just coming from the cathode and hitting this, and then it kind of recycles itself again. And so scientists really weren't sure what this was quite yet. They just know it's coming from this metal, this mysterious ray. The physicist J.J. Thomson was one of the scientists that did experiments using the cathode ray tube, and his famous experiment, the charge to mass ratio experiment, is what we're going to talk about today. He actually did 3 experiments. So his first experiment, what he did was take these rays and take this tube, and he wanted to see if the negative charges can be separated from cathode rays using a magnetic field. So we have our mysterious ray. Okay, imagine it's inside the tube, and we have our magnetic field. Let's say it's into the page. Remember, X is into the page for the magnetic field here, which has the symbol B. And remember your hand rules from Unit 2. What would happen if this ray was going into there? Okay, if it's negative, we use our left hand, so our thumb points in this direction right here, and our fingers into the page. So what's going to happen is this ray would bend down, okay, using that palm as our force, our magnetic force here. And this is exactly what he found. Remember, he found that it bent this way, and so he concluded that there was negative charges in this ray. So he wanted to kind of test that theory one more time, a different way. So he did a second experiment. So his second experiment was taking that ray again, and let's put it through a electric field. And so we can create an electric field using parallel plates. Let's say that we made the top plate positive, and we said that the bottom plate is negative. Well, according to our law of electrostatics, if this is negative, it should go to the top of the plate. If it's positive, it would go to the bottom. And so what he found was that this beam was attracted to that positive plate. So that tells us that the nature of this charge was negative. So we give it a negative sign. So he knew that. Still not really knowing what these rays were. The third experiment is the one that he's most famous for. It's the charge to mass ratio experiment. And so he looked at putting these two ideas together, looking at how an electric field and magnetic field kind of work in conjunction. So what we have to have here is a cathode ray tube, and this is kind of what his looked like, simplified version. And here we have our cathode and our anode, and we have our voltage source, a variable voltage, and let's put a parallel plate there, and let's put a parallel plate here on the outside. Let's make this one negative, let's make this one positive, okay? And let's have a magnetic field going into the page, and so we could create those using just a solenoid on the outside. So what he did was manipulated these two fields, the electric field and magnetic field, their strengths, so he made them equal. And what he noticed was that this ray would go straight through unaffected. And so if we look at the physics behind it, what we have is that principle, and the principle that applies to that is balanced forces. What we have. So we have balanced forces acting. And so let's look at a free body diagram of those rays. And so at the top, we have an electric force, and then acting down would be our magnetic force that we showed for experiment 1 and 2. So these are the same. So we get an electric force here equaling a magnetic force because the forces are balanced. And so we know electric force is defined as EQ from unit 2, and then magnetic force is QVB. So you can see that the Q's cancel. He knew the electric field strength, okay, and he could, or knows, the magnetic field strength. And so what we can do is find out the speed that those rays are going. So that's kind of what he did for the first part of the experiment. Okay. And so what he can do is calculate the speed, and he actually did that. Then what he did was shut off the electric field. And so if we shut off the electric field, so let's just remove this electric field right here. Okay. Take it out, and then we just have a magnetic field. And so this is our new ray. What's going to happen? Well, the magnetic field is going to bend it down according to our hand rules. Why is it going to bend down? Remember, it's negative. The thumb points in the direction that the ray is moving, fingers into the page, and so your palm faces down. So we have a magnetic force acting on that. And so if we look at the mathematics behind it and use the physics principle, so we have two principles when we're talking about the charge to mass ratio experiment. One is unbalanced forces. The forces are no longer balanced, and so the unbalanced force causes the ray to bend. And so the net force is the magnetic force. That's the only force acting on this particle. Gravity is there, but gravity is so small because remember, it's an electron, has a really, really small mass. It's not going to affect it. But your net force is mass times acceleration. And now the fact that this moves in a circular type shape, it's centripetal force. We're going to call that centripetal acceleration. And your magnetic force is QVB, which we've seen before. Remember, the definition for centripetal acceleration is v squared divided by r from physics 20, and then QVB right here. So what happens is your velocity cancels out, and we have, just go moving it over here, mvr qv. Now, he knew the magnetic field strength, he could measure the radius, he calculated the velocity using the electric field and magnetic field when they were equal from the last part we did. But he didn't know the mass, and he didn't know the charge. He didn't know what these were yet. And so that's where we get that charge to mass ratio. So I'm just going to do the algebra here. You get charge over mass, and that equals the velocity and divided by your magnetic field strength and your radius. So this equation right here is known as the charge to mass ratio. We knew the velocity, we knew b, we knew the radius, and so he calculated this charge to mass ratio, and he expected this number to be extremely big, okay, extremely large, or he calculated or found out that it was extremely large. And now it should be pretty big. If you could think of 1 kilogram of just electrons would have a huge amount of charge, and this number was around 1.76 times 10 to the 11, I believe. 10 to the 11, yeah. 10 to the 11 coulombs per kilogram. Okay. And that was the charge to mass ratio for an electron. Okay. Still didn't know what they were yet, but he knew that the fact that this rays or these rays were produced depending on the type of metal that he chose here, all the things, the same things happened all the time, and so he concluded that these rays were pieces of matter, okay, part of the atom. And so if we go back to the Dalton model was the model with the billiard ball model. So this is what he thought, okay? So Thomson said, okay, these are charged particles, so the atom must be electrical in nature, and the fact that it's electrical in nature means it has a positive charge and a negative charge, and the reason for that is because it has to be neutral. And so this is the model that he came up with, that this sphere would be like the positive stuff, positive fluid, and then embedded in it were these negative particles that he found using the charge to mass ratio. And so this is known as the plum pudding model. Okay? And not really sure what plum pudding is, but you can imagine some pudding with stuff inside. I like to call it the raisin bun model or the chocolate chip cookie model. But chocolate chip cookie doesn't give us a spherical shape. Imagine a ball of chocolate chip dough. So that's his model. That's how he found the charge to mass ratio. And looking at those two principles, balanced forces and unbalanced forces, enabled you to do that.